Hello, PreCalc. Here we are with 9.6, counting principles. Alright, jumping right into it. If we have 8 pieces of paper, numbered 1 to 8, and placed in a box, one piece of paper is drawn out from the box and its number is written down. And then the piece of paper is replaced in the box. It's put back in the box. Then you draw out a second piece of paper from the box and its number is written down. Finally, the two numbers are added together. How many different ways can a sum of 12 be obtained from the numbers 1 through 8? So we could go with 4, 8, 5 followed by 7, 6, put the 6 back in the box, and then we get 6 again. You could have 7 first and then 5, or 8 and then a 4. So that's 1, 2, 3, 4, 5 different ways that we could come up with 12. The counting problem in example 1 can be described by saying that the random selection in example 1 occurs with replacement, which allows the possibility of choosing 2 6s. Okay? Because you pick the 6, you put it back in the box, and now you have the possibility of picking the 6 again. Now look at example 2. 8 pieces of paper, numbered 1 through 8, placed in a box. 2 pieces of paper are drawn at the same time. Okay, the numbers are written down on a piece of paper and totaled up. How many different ways now can we get a 12? If we're reaching in and grabbing both pieces of paper at the same time. Well, we still have our 4, 8. We still have 5, 7. We no longer can get the 6, 6 because we don't have 2 6s in the hat, right? Or in the box. We just have 1 6 in there. We're grabbing both at the same time. So we could have 7, 5, and 8, 4. And now we're down to 4 ways. Okay? Examples 1 and 2 describe simple counting problems in which you can list each possible way that an event can occur. When it is possible, this is the best way to solve a counting problem. However, some events can occur in so many different ways that it is not feasible to write out the entire list. In such cases, you must rely on formulas and counting principles. The most important is the fundamental counting principle. Let E1 and E2 be 2 events. The first event, E1, can occur in M1 different ways. After E1 has occurred, E2 can then occur in M2 different ways. The number of ways that the 2 events can occur is M1 times M2. The fundamental counting principle can be extended to 3 or more events. If you have 3 events, then it's M1 times M2 times M3. Okay, how many different pairs of letters from the English alphabet are possible? Alright, so pair. We're picking 2 letters. How many letters do we have? 26. So you have 26 possibilities for the first spot and 26 possibilities for the second spot. And 26 times 26, we have 676 pairs of letters. In a certain state, automobile license plate numbers consist of 2 letters followed by a 4-digit number. How many distinct or different license plate numbers can be formed? Okay, so it starts off with letter, which we said is 26. And then we have 4 number spots. Okay. How many different single-digit numbers? Well, you're thinking 1 through 9, that's 9, but we can also go 0. If we include 0, 0 looks a lot like O. So maybe sometimes you don't include 0, but we're going to say we do. So that would make 10 numbers then, 0 to 9. So we have 26 possibilities there, 26 possibilities there, 10, 10, 10, 10. All right, multiply that all up. We just did 26 times 26, and then put 1, 2, 3, 4 zeros behind it. $6,760,000 license plates. One important application of the fundamental counting principle is determining the number of ways that n elements can be arranged in order. An ordering of n elements is called a permutation. A permutation of n different elements is an ordering of the elements such that one element is first, one element is second, one is third, and so on. How many permutations are possible for the letters A, B, C, D, E, and F? Okay, when order matters. Order matters. All right, so we have 6 letters. So if we pick one out of those 6, we got 6 possibilities for the first spot. And now I've taken one of those, and now I have 5 left. So I have 5 options there for the second spot. And then we have 4 options left for the third spot, 3 options left, 2 options left until we're left with a 1. And look at that. 6, 5, 4, 3, 2, 1. That's going to be 6 factorial. Or there's 720 different permutations there. The number of permutations of n elements is n factorial, as we just discovered. In other words, there are n different ways that n elements can be ordered. It is useful on occasion to order a subset of collection of elements rather than the entire collection. For example, you might want to choose and order R elements out of a collection of n. Such an ordering is called a permutation of n elements taken R at a time. And that's when we see the NPR like we saw the NCR yesterday. So the number of permutations of n elements taken R at a time is n factorial over n minus R factorial. A coin club has 5 members. In how many different ways can a president and vice president be selected from its members? Okay, so order matters. President, vice president. Okay. We have 5 members. We're taking 2 out of those 5. So we got 5 factorial on the top over 5 minus 2 factorial. So we have 5 factorial over 3 factorial. And if we kind of simplify this down, 5 times 4 times 3 factorial over 3 factorial. Cancel. We got 5 times 4, 20 different ways. 20 different ways you can come up with president, vice president out of a group of 5 people. Remember that for permutations, order is important. So if you are looking at possible permutations of the letters A, B, C, D, taken 3 at a time, A, B, D, and B, A, D are counted as different because their order of the elements is different. Suppose, however, you are asked to find the possible permutations of the letters A, B, C. The total number of permutations of the 4 letters would be 4 permutations taken 4 different ways, or 4 at a time. However, not all of these arrangements would be distinguishable because of the 2 different A's. Okay? To find the number of distinguishable permutations, you can use the following formula. Suppose a set of n objects has n1 of one kind of object and n2 of a second kind and n3 of a third and so on. Then the number of distinguishable permutations is n factorial divided by n1 factorial times n2 factorial times n3 factorial and so on. So find the number of distinguishable permutations in the word Mississippi. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different letters. So there's 11 different letters, 11 letters. And we have 1m, so 1 factorial. We have 1, 2, 3, 4 i's. We have 1, 2, 3, 4 s's. And we have 2 p's. So we've got 11 factorial divided by 1 factorial times 4 factorial times 4 factorial times 2 factorial. So 4 times 3 is 12 times 2 is 24. So we got 1 times 24 times 24 times 2 on the bottom. Where is our... There's our exclamation mark under math probability. So if we wanted to make it look just like this, alpha y equals fraction bar 11 factorial, and then we had 1 times 4 times 4 times 2. For 34,650. Otherwise, we had 24 times 24 times 1 times 2 for 1152 on the bottom. And then we could type that in, and we'd still get 34,650. When you count the number of possible permutations of a set of elements, order is important. As a final topic, you will look at a method of selecting subsets of a larger set in which order is not important. Such subsets are called combinations of n elements taken r at a time. For combinations, ABC and BAC would be considered equivalent because they have the same 3 letters. And the order in which those letters are listed is not important. So you would only count one of the 2 sets. A common example of how a combination occurs is a card game in which a player is free to reorder the cards that they have been dealt. Okay? In how many different ways can 3 letters be chosen from A, B, C, D, E when the order of letters is not important? Okay? So we could go A, B, C, A, B, D, A, B, E, A, C, D, A, C, E, A with a D, E, We can start with B first. B, C, D. B, C, E. B, D, E. And then we would need C, D, E. So we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways. Or we had 5 letters and we were taking it 3 different ways. And from our arrangement yesterday, with this, we know that's 5 factorial over 5 minus 3 factorial. And the only difference is now we have the times 3 factorial again on the bottom. Okay, the combinations has just that, 5 minus, and it doesn't have the times that same one again. So 5 factorial over 2 factorial times 3 factorial. And if you remember our shortcut from yesterday, how this should work out is to be 5 times 4 over 2 times 1. 20 over 2 is 10. Okay, the number of combinations, like we just looked at there, is the same thing we looked at yesterday. N factorial over n minus r times r factorial. So it's kind of weird that yesterday they gave us this, they showed us this, they had this listed in the notes and we used this, and then here they taught us the combinations part today. Note that the formula for n number of combinations taken r at a time is the same for our binomial coefficients. To see how this formula is used, solve the counting problem in example 8. In that problem, you are asked to find the number of combinations of 5 elements taken 3 at a time, and the number of combinations is 10. So just like we had just done. Last ones. For a certain experiment, 4 students are randomly selected from a class of 20. How many different groups of 4 are possible? So we had 20 students. We're taking 4 at a time. Okay. And we'll have 20 factorial over 16 factorial times 4 factorial. And if you remember our shortcut from yesterday, you're going to have the first 4 terms of this one. 20, 19, 18, 17. Because then the 16 part cancels, and then we have 4 times 3 times 2 times 1 on the bottom. And we'll have 48, 45 different groups. Okay. You are forming a 10-person committee, 9 women and 12 men. The committee must have 5 women and 5 men. How many different 10-member committees are possible? So we're going to need to figure out our probability for the women and the men and then multiply them together. So we have 2 kind of separate ones. So for the women, there are 9, and we're taking it 5 different ways. And then on the men's side, there are 12 to pick from, and we're still picking 5. And to do this on the calculator a little bit faster, we can go to Math, Probability, and we got NPR and NCR. We're doing combinations. So we have 9C5 for 126. And then math, probability, and we have 12 C5 for 792. Multiply those together, and there are 99,792 different 10-person committees that we can come up with. When solving problems in counting, you need to be able to distinguish among the various counting principles in order to determine which is necessary to solve the problem correctly. To do this, ask yourself the following questions. Is the order of the elements important? Then you need a permutation. Are the chosen elements of a subset larger set in which they're not important? Then we're using combinations. And does the problem involve two or more separate events? Then you'll need the fundamental counting principle. Combination, or the number of total things for A times the number of total things for B. So there we go, folks. Best of luck to you, and we'll see you next time.